they align it. Sorry. And they train, for example, UNet model to align directly with this collected evidence. But in this work, we use different approach, especially when we have this a certain or very noisy CAM. So using thresholds is an additional hyperparameter, and also it's bad because threshold those CAMs are threshold in them is very difficult. They vary from image to image, and also they have different distributions. So finding the optimum threshold is really impractical. So our main contribution is to provide a different way, and here we use sampling mechanism. So instead of taking performance thresholding or taking like a huge like a mask, for example, and align it with our model, we actually sample only one pixel, randomly one pixel from the CAM, considered as foreground, another pixel here considered as a background. And this sampling is based on the magnitude of the activations. So typical assumption on these CAMs is that the higher the activation, the more likelihood that that pixel is a foreground. And if the activation is very low, it's more likely to be a background. So we use the same assumption, but instead of relying for certainty on only a few pixels, we drop that certainty and we say we sample based on those activations. So we use stochastic sampling at each iteration to sample evidence as foreground and background. You can see this as extreme dropouts. Usually dropouts, we have like a signal, we drop like only parts of the information and keep only a small part, but in this case, we almost drop the entire signal, we keep only like 2 pixels. And the reason for this is to avoid overfitting, because if we predefine like fixed proposals or regions, we go under the risk of fitting those regions and which are possibly the wrong regions. So we avoid that explicit fitting directly or at once of those regions. And instead, we sample randomly the pixel to avoid quickly overfitting those regions. And also, one of the reasons is to give time or to the network to learn patterns and let's probably consistent patterns to emerge. Because if we quickly learn to fit, for example, this CAM, we will obtain probably the same CAM but at high resolution. So there is really no interest. And the idea here to only select randomly few pixels is to give, for example, convolution filters to adapt and probably spike somewhere else in regions that are similar to those pixels that we randomly select. But we see an ablation study at the end that shows the benefits, for example, from using fixed seed compared to this random or stochastic sampling. So that's what I was saying. So the sampling here is based on the activations. We consider entire CAM as legitimate for sampling, but we weight each pixel using the activations. And this is similar to use like multinomial distribution on the CAMs and sampling using that distribution. Different again from, for example, learning with seeds in weakly-supervised segmentation. Here, at each iteration, for each sample, we select new pixels, and we forget about the previous ones. Okay, so for each sample, each SGD step, we select 2 new random, like pixels, one foreground, other background, and then we try to fit, align it here with the produced CAMs. So in total, if we look at the entire training session, for each sample, we'll end up using at most the number of epoch multiplied by 2 pixels. Like in our experiments, usually we use 50 epochs, so we will end up by using 100 pixels, which is around 0.001% of the area of the image. So it's almost nothing compared to the image size. And we show that using only this small fraction, random fraction of the pixels, we show that it can largely improve the accuracy of these low resolution CAMs. Sorry. So this is really the main slide in the whole presentation, is the sampling mechanism, or the random sampling mechanism instead of fixed sampling. So once we train our model, at the end we end up with foreground and background, since the objects, you know, are foreground. So this is our final CAM. And in object localization, when we look, for example, to produce a bounding box, there is standard procedure to apply to these CAMs to produce boxes like this. Sorry, like this. So we need first a threshold, and then obtain a mask, and then use some image processing step to find the tightest bounding box that's covered the largest objects. So this is some results on CUB datasets for bird species. So in the first row here, we see the standard CAMs. So as you can see, they spot only a small fraction of the objects. And when thresholded, you can obtain like weird masks that cover the entire image, because again, we will see later that this distribution of those activation are not that good, and finding the optimum threshold is actually difficult. So this is the different architecture. This is VGG16, Inception, and Résumé. And in the next row is our method. So you can see from here we go to our method. You see that the CAM expands to the objects, and also the activation starts to be more strong, like either 0 or 1. And this is due to the learning that we use here, or the loss that we used at this. So this is partial cross entropy, because we end up, when we sample pixels, we will end up with a mask that is partially labeled. Like only 2 pixels are labeled, either foreground or background, and the rest of the pixel is unknown. So we just align those pixels on the rest. We don't know their labels. So we end up with this certain activation maps that expand, as you can see here, for example, expand exactly to the, thanks to the CRF, expand to the boundary of the objects and then stops. So this is the first data set. There's another data set where the evaluation is based on, not on bounding boxes, but masks. And as you can see, for example, here is the same behavior, like CAMs are minimal, like they just activate on small regions, but using our mechanism, we allow to expand to cover the entire object. So just a reminder, so as in our method, we use a base classifier that will help us get the seeds. For example, here we need a classifier, baseline classifier, that help us sample the seeds. It could be any method that produces CAMs. So in other words, like the method is generic, you can plug any CAM method and then train our module. So here we compare to state-of-the-art methods, but also we take some very simple baselines like that produce CAMs as well, which are considered like outdated, especially for example CAM here. And when we add our method or our decoder to this method, which became actually state-of-the-art in both data sets. There are other results. This is the one metric, but there are other metrics you can find in the paper. So we look into how our CAM behaves when we vary a threshold. As I said before, to find, for example, the boxes, we need to threshold the CAMs. And there is a typical behavior of CAMs, standard CAMs, when we came to this thresholding. So in orange are standard CAM, and in the x-axis is the threshold that we vary, and in the y is the localization performance. So as you can see, the higher the threshold, the more the localization drops. In other words, good thresholds are concentrated around zero value. They are small threshold that's yield the best localization. And we looked to the distribution of the activation to see why this is. And what we found is that most of the activations, even if they look like they spike here, this is just an illusion of the coloring, the matplot coloring. But in reality, all the activation are almost around zero. So that's why the best threshold usually is very small. So one of the things that we expect in this distribution is has two modes. Like the first mode is around 0 to represent the background, but another mode around 1 to represent the foreground. But it doesn't seem the case in standard CAMs. But in our method, it seems like it tends toward that direction. Like there is high activations around 0, but also starts another peak here around 1. But this peak, or the magnitude of these peaks, are dependent on the size of the objects. Like if the foreground is small, you end up with small activations here. But if the background is, for example, large, you end up with more activation. And we can see this in another data sets where there is clear spike on the foreground because the objects also there are large objects, so we end up with more concentration of the distribution in around 1. But also there is a background. So in other words, our method now is more certain on what is foreground and what is background. And this is mainly due to the partial entropy, cross entropy, sorry, that we use to push the activation to be either 0 or 1. We did an ablation study on different terms to see their impacts. So in the first row here is the baseline, the CAM. And as you can see, when we use like the seeds or the sampling pixels, we immediately quickly improve the performance in both data sets. Adding CRF and the size constraints also helped improve, but combining all of them actually yield like large improvements compared to the baseline. So meaning if you have like simple CAM that's produced relatively good localizations, you can actually add large improvements if we add those, simply add a decoder and train it using these terms. There are some drawbacks to this method. One of them that probably worth mentioning here is the dependency of our method to the base CAM. So if the CAM is good and provides good localizations, even if like partial localization, you can actually get good performance using our method. But if the CAM is bad, like in this case, for example, so here we want to localize the target is the license plate. It's not the car. Okay, so it's this thing in green. So the object that we should look here is the license plate. But as you can see, the base CAM activated almost the entire car. So it's understandable here because the object is very small, and wherever there is a license plate, there is a car, and vice versa. So it's difficult even for the CAM because the label is weak, so we don't know really what we're looking for. But the real target here is the license plate, but the CAM spikes all over the car. So when we use our method to sample from these activations, well, because the activations are wrong to begin with, or we sample from the wrong labels, and then we end up with activating an entire car here. So if the CAM is really poor, our method cannot rectify that. I mean, it will go in the same wrong direction because we are training using the wrong labels. And this happens actually in all the architectures. So this is one of the drawbacks. In terms of runtime, because we are adding a decoder, we add more parameters and potentially add also more runtime, but compared to the average methods that we compare to, we are actually not that slow. You know, we are competitive also in terms of runtime. So there is no really like it doesn't very slow the inference time. So this is the overlook of the method. We have been also working on histology for some time now, and we thought it would be a good idea to see how this method or this approach perform on histology, especially that we know that typical CAMs are extremely poor in this type of data, because we'll see later like why. So we know, so it's another test of this method on very noisy CAMs. So in natural images, usually, as you saw before, like CAM method can spot relatively the objects, or at least parts of the objects. In this type of data, the objects are actually difficult even for a human eye. So we evaluate this on 2 datasets. And some of the properties of this type of imagery is they are microscopic images. And one of the difference between this and natural images is that objects are not silent, meaning that you can easily confuse the foreground with the background. And one of the reason of this is the similarities in terms of colors. So you really need an expert to you know, tell what's for example cancer, what's a normal tissue. Another issue is the structure. Like in natural images, usually objects have a common structure. For example, a car, if I say the word car, you know, in your mind, you know what's actually how it looks supposed to look like. Or a dog, for example, there is general structure of those objects that are repetitive in the images and probably helps the network spot them. In this type of imagery, there is no really typical structure. They are almost arbitrary structures. And another difficulty in this type of images is the coloring or the stains. You can see probably here in this row the impacts of the stain. So usually those tissues after the biopsy, they were colored using some procedure, and that type of coloring affects how, you know, the image will look like under the microscope. So this actually brings an additional difficulty to deal with these images. We use relatively the same method, but we adapt it, also remove some terms, but we adapt it to this type of data. In particular, we use negative samples. So before we use some evidence from a classifier about positive regions and negative regions. In medical images, mostly, sometimes datasets have fully negative samples. For example, you can have normal samples, like they are not sick, and other samples that are, for example, sick or have some diseases. So our idea here is to exploit negative samples because they have actually a lot of information in terms of localization, because they tell us, if I show you, for example, an example, tell you this is negative. Actually, I told you like what's a positive objects doesn't look like. You already have the information that, or network have the information that what's not an object. So it's prevented from spiking on those regions as, for example, cancer or positive. So the idea is to exploit these negative samples in very simple loss. Our loss is something like this, looks like this. So if the sample, and we know that beforehand, you know, in the data sets, we know that these samples are fully negative. So if the sample is negative, it means that we should set the CAM to 0. They shouldn't activate because there is no cancer, there's no region of interest in that image. If it's not fully negative, it means that it contain, you know, region of interest in addition to some background. And in this case, we use our sampling or our evidence from the pre-trained classifier. And loss looks something like this. So this first term deal with fully negative samples. So we push the foreground to the background to win compared to the foreground. If the sample is actually not fully negative, we use the collected evidence from foreground and from the classifier. So the general architecture doesn't change. Only difference is, or the main difference is using these negative samples. And also we didn't use the size loss and the CF loss, but we showed that using this simple information, we can actually get a large improvements compared to state of the art. So we evaluate our method to different methods, or weakly-supervised methods, on two datasets, GLASS and chameleon. GLASS is somehow simpler compared to chameleon. Chameleon is more difficult, and you can see this from like the average performance here compared to this one on different architectures. In total, our method actually yields like better performance on both datasets, and in this case, we use also like a simpler method, that is CAM, as the source of positive and negative evidence. Similarly, we conducted ablation study. So this part here is the same as that we saw in natural images, except it didn't have like fully negative samples. This dataset doesn't have fully negative samples. The other one, on the other hand, has said that is fully negative, so it helps determine what's, for example, background and what's cancer. And using that, actually we help like increase with large margin the performance. Using positive and negative evidence from the classifier in this dataset specifically didn't really help much, again because the baseline CAM is extremely poor. So what's helped here really give this large margin is actually the negative sets. So this shows actually the impact of using those type of samples. We did also an interesting ablation to compare static selection of seeds. Like before we said, okay, we randomly select, but what will happen if we fix the seeds? And this is similar to the case of learning with seeds in weakly-supervised segmentation, where, for example, the user clicks on positive, say this is positive, this is negative. So this is similar to this static selection, and this is ours, like using random selection. When we use actually static compared to random, actually there is actually a drop in all the cases, suggesting that actually randomness in this scenario helps improving the performance. Given that actually those CAMs actually to begin with are actually extremely noisy. Okay, so there's that as well. So the random, we believe that this random selection somehow prevents overfitting to the noise in the image, and gives probably more chance to the network to learn consistent patterns instead of following the randomness in the noise. So this is some of the visual results that shows, for example, so here we have the input images on these 4 datasets, and the ground truth means the mask that we should produce. And this is what CAMs actually produce in those images. You know, it spots somehow probably some of the important regions, but it's still actually extremely noisy. So this is was actually a good exercise for this method. And when we use ours, again, if we try to feed directly those activation, we will end up something like this. Again, so there's no reason to deviate from this. But because of the randomness, it helps like consistent pattern to emerge. Okay, so it doesn't activate all over the images, but actually spotted meaningful patterns in the. And this is probably one of the properties of the convolutions. Was shown in another paper, that's probably titled Deep Image Prior, that convolution prevents noise to go through the network. So if you have, for example, noisy image and you try, for example, to reconstruct it, it will produce a smooth image. So even if the pixels or the Cs are actually noisy, convolutions will try to stay consistent in terms of activations. So this is the first. This is the second data set. So the top row is normal. So there's no cancer in it. So it should be blank like this. There's no activations, which you see in our method, and also full supervision. So UNet here is the full supervision when we have the masks in the training. You can see the cam here also activated also on the normal, which shouldn't be the case. This is the second, the last two rows are cancerous regions. So there is some activations. So there's some regions that should be activated. We see this in our method, clearly in our method, and also in full supervised method. But again, the CAMs are activating almost everywhere, but there's more activation around this region. This probably explains why our method spikes also here. Because again, sampling is based on the activations. So these regions here are more likely to be sampled during the training compared to this one or this one where there's no activations. Okay, so this is the last slide. So the advantage of this our method is it's weakly supervised, so there is no need. We don't use only the global annotation. There's no need to add extra supervision. It's generic. You can plug it on top of any CAM method to fine-tune or refine the localization or segmentation. To improve here, yeah, the task here was to improve the localization and also the segmentation. We show empirically, we don't really have hard proof, but we show empirically that in this scenario, when we have like noisy signal, supervisory signal, it's better to use random stochastic sampling of evidence from that signal instead of like learning with fixed or predefined proposal from that signal. So that's probably the main message in this work. The concept of the method, I think you mentioned this, is the dependence of our method to the classifier or the quality of the CAM in the classifier. So if the base CAM is extremely poor, our method will not actually rectify that. So if you have like CAM with relatively good activations or initial localization, using our method can help actually refine the localizations. Also, we know that when we sample, we can sample the wrong labels. So there is a huge risk to feed noise or wrong labels to the network. So we need actually like a better way to filter out the wrong labels. So we are currently working with another PhD students in a different, relatively close but different scenario where we can estimate an additional information that is the certainty of that label in that pixel. So we can use that, for example, certainty to discard irrelevant regions or potentially wrong labels from the learning and fits only the more likely pixels to hold the right label. Okay, so you can find both papers on arXiv and also the code on GitHub. You can check it out, and yeah. So thank you for your time. And if you have questions, happy to answer.
Okay. Thanks, Soufiane. I see. Are there any questions from the audience, or? Yes, so Philippe Giguère, please go ahead.
Thank you. First of all, very interesting talk. Very, very interesting. I have a question. Like the examples that you show are usually like one class, basically birds, and then background, so foreground, background. what happens if you try to extend it to more complex scenes where you have several classes of object, like, you can imagine like a cityscape images.
True. Yeah. So indeed, this is like object localization. Usually the task is only one object in the image for localization. We have discussion actually about multi-label, like in object detection, when you have multiple objects in the image. I think the extension is straightforward. There is no lots of things to do. The only thing is that the CAM that you are using, because if we have multiple objects, it means we have multiple CAMs, like each CAM for an object, and we can easily extend the number of CAMs here. For example, if we cityscape, I think there is like 20 class or something. So we can easily add 20 map here and gather the information from each class, from each CAM. We guide the learning of that map specifically. So the extension from single class to multi-label is almost straightforward. That we didn't try that, but it should on paper it should apply. It should go like this way, because we can from for example, if you have like bike here, this is the CAM of bike. You can extract the seeds and train the bike map here. If you have, for example, there is a car in the image as well, you have also an additional CAM of cars, and you can extract as well the same sample of different seeds to align it with the car map here. So I think the extension is really straightforward, but we didn't try it.
Okay.
Because I think there is less, I'm not really expert in object detection or like, but I think there is less work on CAMs for object detection. Probably they use different, I don't know if there are experts here, but there are like probably different approaches for that. I remember we tried on Cityscape for another paper on CAMs for patents, and the CAM method actually almost failed to spot objects, specifically for data sets, because usually classes coexist almost on all the images, like pedestrians, cars, and trees and all that. They always are presented in the image and make the CAM it wasn't unable to discriminate between objects. So that's
I'm not surprised, because it's a very difficult problem when you switch to Cityscape.
Yeah. But I'm not sure how it will react on other data sets, like when there is probably in different scenario. Yeah.
I don't know if I have time for follow-up questions, because we did some work like a while, and we used something called Wildcat.
Yeah.
And which I think is basically you have several planes for each class. You have several planes, and then you sort of like combine them.
Yes. Yeah. Okay.
I don't know if it's something that you can extend. Yeah, you have it like Wildcat right there.
Yes, actually, Wildcat is like a very. If you are familiar with the gap, like global average pooling, it's just the pooling at the end, how they do it. They do it differently. Okay. But I don't know if your question is, did we use that, or is it relation to that paper?
Basically, would it be a possible direction to research by using, because if I remember, they use several feature maps per class, like in the global average pooling, and the end is like one layer, one class. If I remember, Wildcat was several layers at the same time.
Yeah, but actually, they use like for each class. Yeah, indeed, for each class they model. They call it multi-model. Like for each class they have like several maps, but at the end they average them using some convolution, and then they obtain only one CAM, and they will end up in this scenario. So if you have like 3 classes in the data sets, we end up with 3 CAMs as well. But if we can apply that as well as our baseline, like our base to sample from them, from either from the last CAM, like the single CAM, or probably the those models or modules that they before. They use for probably 5 or 6 to represent each CAM and then average them. But typically we use probably the final CAM if we want to use wildcats.
Yeah, just give you like kind of more flexibility by having several layers. Anyway, I absolutely have to go. So, but thank you very much for your questions. It was very interesting.
Thanks. Thank you very much.
Great. So, Christian, you have a question?
Yeah. Thanks for the presentation. I thought it was well done and very interesting. So my question is for the model which has the size prior and the CRF prior. So I'm sorry if you mentioned it. How do you determine the size for the foreground, and how do you like typically in CRF you have some parameters like the impact of color or distance, or even the weight of the binary terms. So how do you determine those?
Okay, yes. So yeah, for the CRF, there are actually, we use bilateral filtering. So there's a term of colors and also the spatial locations. But we use like there's only the hyperparameter to fix is lambda, and also the filter hyperparameters, but we use them. We use the same values as Ismail paper. So this is like the lost CRF proposed in another of Ismail paper, and we use the same hyperparameters.
Okay, are these hyperparameters tuned per image, or are they fixed for the whole data set?
No, fixed for whole data sets, yeah. And we use them actually for both data sets, so we don't really change that. But but for the size, actually the size is unsupervised. It is just a prior. So there's no, we don't know the size, of course, as in the images. We just say that like if we take an image, we know that there is objects and also that there is background. So we need to push both elements to have like large size. And this like why we did this, because to avoid this, for example, this scenario where the background dominates the foreground. Like in this scenario, you have like small size of the foreground, like very small, and the rest is background. So this is actually shouldn't be the case. We just say we want the size of the object to be large as possible, but also the background to be also large as possible. And of course, the optimal on this, like if they are half and half, but in practice it shouldn't be the case, because size change from image to another. But because of using the CRF and also this guidance at pixel level, these ones will prevent this trivial solution like half and half. So because they will violate, for example, the CRF, because the objects probably will expand outside the boundaries, or because the seeds that we sample are not hitting in the right place. So in this case, it won't happen actually. I mean, we didn't see this in
because looking at this particular equation, I'm not quite sure what does it mean, like the sum of greater.
So I didn't probably talk about this in detail. So here we model the outputs here as two maps. We explicitly model the foreground, and we model also the background. So if we looked, the size is actually is the sum of the activations of each map. For example, this is one of them S0. Like, sorry, the R1 and R2, like the R1 and R2. So the size, you can see it as like the sum of the activations in that scan. And it is.
But isn't the sum always greater or equal to 0? I mean, I don't understand how you can violate this constraint, because I'm guessing that.
So if we see it like this, but the idea is to use log barrier to try to push this the optimum. The optimum of this, like yes, when you do the sum, the optimum of this is like if the higher it is, the more optimum it is.
Right. Okay. So it's more than okay. So there should be maybe a greater or equal to some minimum value, right? So that it doesn't.
No, it's when you optimize this, because the optimum should be like large size. If it's close to zero, it will be penalized. Like the further you are far away from zero, the lower.
Okay.
So if the network says, oh, the size is like let's say the size is between 0 and 1, because it's normalized. Okay, it's between 0 and 1.
So there is some sort of penalty that pushes it to be not only greater or equal to 0, but also away from the 0 as well.
Exactly. Like, it has to be like very large. So the larger it is, the lower the penalty. If it gets closer to 0, you get a higher penalty. Yeah.
I get it. Okay, thanks.
Yeah. Okay.
Question on my side. So getting to this figure that we have here. So you're using, and maybe it's a clarification as well for Christian's question. There's really a two-step training, right? So the first stage where you're training the CNN, the 2D CNN on the left side of this image, that's in
classifier,
red, in red. And that is the term used for that is the first term of the loss is
exactly
centric stuff. And so once that is trained, then there's a second phase where we're kind of adapting or training the decoder part on the right side of the image based on the sampling process, and then the other terms come into play. So it's really a two-stage process. But the question I had for you, the initial motivation. So you're saying that it's because of problems with interpolation. I'm just wondering, is this problem is large if you have a smaller 2D CNN? For example, a lot of people are working on applications where they're using something like MobileNet V3 or OSNet. They're really compact CNNs. I'm just wondering what would be the impact? What would be the impact of this method if you were using a smaller model? Because probably the interpolation problems would be smaller, but maybe the CAMs are not as well defined. I'm not sure, but what is your feeling on the applicability of this to smaller models? Because a lot of your experiments are based on like ResNet 50, Inception V3, which are bigger CNN.
I think bigger in terms of parameters, but I think it's because I think I'm not really familiar with smaller networks, how they are organized, because you can make, for example, a ResNet thin simply by removing filters, but it will not change the resolution of the final CAM. Like you will obtain the same resolution if you drop filters. But again, I think we need to look like how like the final resolution of those models, how they look like the CAMs at the end. But I didn't experiment with them. But I have no idea like how they
why they wouldn't provide.
Because if they are, but again, if probably they are more oriented to classification. I don't know if they are designed for producing, or they can probably produce sideway like the localization as well. I can't really tell like what's, but I think really the question should like look to the quality of that CAM. Like if it's not really directly related to the complexity. Like if you don't know the model is small or big, I think the question would probably go to the CAM. Is it like good does it provide like a good localization or? But I didn't really see these models here, to be honest.
Yeah, I guess my question is whether
yeah.
we would get the same kind of benefit with a smaller model, which you know, has like less layers or whatever, and less parameters, and you would have probably, I'm not sure if you'd have less of an interpolation problem there, but it seems like
probably, yeah, because you need to modify the architecture, I think. Because this is actually what people do in practice. So I said like usually the downscale factor is 32, but in this type of application, people change slightly the architecture to end up with smaller downscale factor. Like they go to 16 or 8. So you end up with relatively not really big CAM, but not 8 by 8, probably 14 or 24, something like that. Okay. So like they, for example, they remove some downsampling or they make convolution. It's preserved somehow the size.
Yeah, and there are other literature that have tried to, I guess, produce better, you know, larger CAM.
Exactly. Yeah. There's, I think, one paper. I think we cited in the paper. There's one work that's explicitly designed. I think it's called dilated networks.
Yeah.
Explicitly designed the new architecture that doesn't have this strong or higher downscale factor. So the aim is actually the figure that I present here is from the paper, if I remember correctly. This is from dilated networks. They tried to change the convolution with another type that's somehow preserve the resolution, but this will come at cost of adding more computations and memory usage. So you will have like large feature maps, which actually we are also doing in our like our work, because we are adding decoder that's try to upscale gradually the features. So we are adding also computation, but we try to guide this at least at the end. In their case, it's like weakly supervised. That's it.
Thanks, Soufiane. I see Christian has another question. I'm not sure if it's his old hand or a new hand that's being raised.
No, I forgot to lower my hand. I have no other questions.
I'm just wondering if there are other questions for Soufiane. I think it's pretty late. We've been here. I think probably if there are more questions for Soufiane, it could be taken offline. And as he was showing in his last slide, there's code and there's papers.
Oh, yeah.
So if you felt like trying these techniques, you could go right ahead. So if there are no other questions, then well, thanks for attending, and I guess we'll look forward to the next seminar in 2 weeks. Great.
Thanks, everyone.
Goodbye.
Thank you.
Bye.